Hello and welcome back to Math 301 Introduction to Combinatorics at CSU. Today we'll be talking about the basics of graph theory. We will be doing a lot more graph theory later in the course, but this video is just to introduce the basic concept of a graph and how useful it is in combinatorics. So a graph consists of nodes or vertices or points that we draw in the plane and edges that connect some of the nodes or vertices. For instance, this graph has 5 nodes, 1, 2, 3, 4, 5, and some edges between them, but not all pairs of nodes are connected by an edge. Here was an example of a graph we had in the first video on the handshake problem, and in this case, all of the nodes are connected by edges, so this is called a complete graph, but this one is not complete. Here's another example of a graph. It has 6 nodes and some edges between them. This one's called bipartite because the nodes are sorted into a left column and a right column, where the edges only go between the columns and not within a column. So there's lots of different types of graphs, and the way they come up is in many different applications, mostly related to networks. Social networks where the nodes indicate people and edges are connections between the people, like if they're friends on a social media network, or electrical networks with wires between them, or traffic networks between cities, roads connecting cities or bridges. There's so many different networks that we study in everyday life, and graphs give us a mathematical model and a way of drawing them and modeling them in a simplified way that applies to all the networks at once that we could possibly be studying. So graph theory is very important in combinatorics, and we're going to study a lot of optimization problems in graphs later in the course, but for now let's just establish some basic terminology that really tells us what a graph is. One of the most important concepts in graph theory is the notion of adjacency. 2 vertices are adjacent if they're connected by an edge. So for instance, nodes A and B are adjacent here because they're connected by an edge. B and C are also adjacent, but A and C are not adjacent. Even though there's a path from A to C going through B, it needs to be a one-step path, a direct edge from A to C in order to be considered adjacent. And A and D are similarly non-adjacent. What we want to study is for each node, which nodes is it adjacent to, and that data tells us a lot about the graph. In particular, you can count how many nodes it's adjacent to by a number called the degree. So the degree of a point A is 1 because there's only one edge coming out of it, and the degree of point B is 3 because there are 3 edges coming out of it, and C has only degree 2. So there's potentially lots of different degrees in even just a single graph. Now, when are 2 graphs the same? Whenever we define a new mathematical object, we want to ask, when are 2 objects in this family the same and when are they different? Because that really tells you what fundamentally that object consists of. So here's an example of what I'm going to call the hat graph, inspired by Rachel Priest's previous version of this video. And the hat graph here, if we label its vertices A, B, C, D, E, we can modify it to make a different looking graph by disconnecting A from B and connecting A to C instead. Now on the surface, that looks like a very different graph. The connections are all different, but it's actually the same graph. And the reason is, the way we draw it doesn't actually matter. It just matters which nodes are connected to which other nodes. And if we think of this as a hat, with this being the base and this being the which hat tip, then we can actually think of this path starting from here, going up and then down and then over as being the base of the hat, and then this part as being the tip. Like it fell over and you bent the edges of the hat a little bit. So actually these are really the same graph. In particular, we can relabel the vertices A, B, D, E along the base of the hat and C as the point, and then you can really more clearly see this correspondence between the vertices and why it's really the same graph, just drawn a different way. 2 graphs that have a way of labeling the nodes so that the edges are the same are called isomorphic. Another way of encoding the data of a graph is called the adjacency matrix. It's called the adjacency matrix because 1s are for adjacent nodes and 0s are for non-adjacent nodes. For instance, A is adjacent to B, so in row A and column B of this matrix we have a 1, and in row B and column A we have a 1. Similarly, B and C are adjacent, so we have a 1 here and a 1 here. But we have a 0 in this position because row B and column E indicate that B and E are not adjacent. And we'll see later in the course that actually multiplying the adjacency matrix by itself can help us count walks in the graph, which is a very powerful tool and is why we like to encapsulate this data in a matrix, because then we can use the tools of linear algebra to tell us more about combinatorics. Another way of storing the data of a graph is just by listing out its edges as pairs, as shown here. So this also indicates the adjacency. Another fancy way of doing it is in columns, like A and B form an edge, and so do B and C, and B and D, and C and D, and D and E. So there's lots of different ways of writing down the structure as a picture, as an edge array, or as an adjacency matrix, but they're all indicating the same data structure, really, the same underlying mathematical objects. So now that we know what a graph is and when two graphs are different, we can count the number of different graphs, non-isomorphic graphs, on 3 nodes. If you have 3 nodes, well, you can have all 3 edges between them and form a triangle. If you only have 2 edges, they're going to form a path. You can show that's sort of the only way to do it, because if you disconnect any of the edges of a triangle, you're going to have a path remaining. So there's a path, and then if you have only 1 edge, you'll end up with a disconnected graph. This entire row is a single graph, an edge and a point together. In this case, we have 3 vertices and no edges, and that's okay. That's still a graph, it's just very disconnected. It has what's called 3 different connected components. So we've counted the graphs on 3 nodes, there's 4 of them, but there's other types of graphs as well, and depending how you define a graph, it depends what application you're looking for. So we can modify our graphs a little bit by, say, putting a direction on each edge. This is, say, if you're working with an electrical network where the electricity only flows one way, or maybe there's one-way streets in your diagram of traffic flows. And so sometimes there's directed edges, sometimes you want multiple paths from one node to another, multiple edges even. So it can be sort of super adjacent. This is called a non-simple graph. Simple means that every pair of nodes only has 1 edge or no edges between them, and there's no self-loops either, like here. But you can have graphs that you allow to be non-simple, and then the counts are very different. Now there's infinitely many ways of even just doing your graph on 2 vertices, because we can add as many self-loops and multiple edges as we want. We can also modify a graph to make little edge weights on each edge, where we assign a number to each edge, indicating somehow the resistance of traveling across that edge, or maybe a probability distribution, which can come up in a number of applications. And we'll see these different applications as well later in the course. But for now, you try. How many different graphs, up to isomorphism, actually different graphs, can you find on 4 vertices? And how many with 5? And I'll see you next time.